worst. I really want this one. I can taste it like nothing.
Dr. McFarland, we can't hear you. I think your mic is muted. Dr. McFarland?
Soon as in class, I asked him.
Hey, Dr. McFarland, you're muted.
So sorry about that. I totally forgot to unmute. We just got started. We're going over the definition of conjugation, which is on the board. Conjugation is defined as being a species with at least 3 consecutive atoms that have overlapping p orbitals. All right. So in order to have overlapping p orbitals, we first have to have individual p orbitals on individual atoms. To have that, you need to have at least 1 p orbital left over after hybridization. For example, let's take a look at this molecule. All right, this is an alkene. And if we were to write out the hybridization of all these atoms, sp3, sp3, sp2, sp2, sp3. All right. Now, you know hybrid orbitals are made from s orbitals and p orbitals, right? A maximum of 3 p orbitals, maximum of 1 s orbital, right? With the sp2 orbitals, after you finish hybridization, each one of them is also going to have a p orbital left over. I'm representing that with that double load species. And remember, we've said that pi electrons, right, electrons and pi bonds, they're always found in p orbitals. So this makes sense. And these overlap with each other, and that's what creates your pi bond. Is this a conjugated molecule? Why not? We only got 2, right? We need at least 3 consecutive ones. Now, if we change it a little bit, say we have this. This is a diene. It's got 2 alkene groups. All right. Now, if we look over here, this molecule, or excuse me, this item is sp2. This one's sp2. This one's sp2. This one's sp2. So in this case, we see we have 4 carbon atoms that all in a row have sp2 hybridization, and that means they each have an available p orbital that can overlap. So this would be an example of a conjugated species. It's not the only type you can have. This is just one. This is a conjugated diene. Yep. Now, just because you have a diene doesn't mean it's automatically going to be conjugated. Let's say you had that. That's a diene. And so, yeah, each one of these carbons in the double bonds certainly is going to have an extra p orbital, but it's not conjugated. Why not? Not consecutive, yeah. You have this troublemaker right over here, this sp3 hybridized carbon in the middle that kind of gets annoying. So, not conjugated. So you'll notice that conjugated dienes, they have a pattern. They have alternating double, single, double bonds. And that's something that you can see extended to even very, very large molecules. So within, we're going to see later on in this chapter, within a given couple of molecules that you compare to each other, they can have different degrees of conjugation, right? One of them might be more conjugated. It might have a larger conjugated system than another one. And that can make some differences in both its chemical and physical properties. All right. Any questions so far? All right. All right, the conjugation state will have a role in determining the stability of a certain species, right? Just off the top of your head from what we've been talking about, do you think conjugation would make a species more stable or less stable? More stable? That seems to be pretty much a consensus. Why more stable? What's that? Yeah, very good. The electrons have more room to spread out, right? A pair of electrons would be much happier spreading out amongst 4 p orbitals than it would amongst 2, right? Just like how you might be more comfortable in a big, luxurious house versus a tiny little studio apartment, right? And what's kind of cool about this is you can see this in a couple of different ways. You can represent that delocalization through drawing the orbitals and sort of showing that they overlap and the electrons can move back and forth. You can also represent this by drawing resonance structures. And that's one thing that you see with conjugated species is that they are stabilized by resonance. We took this, right? Let's say we hop this pair of electrons, this double bond over here, to form a double bond between these 2 carbons. And then we hop the double bond up there so that the electrons were just on this carbon. That would give you a resonance structure. It's kind of funny looking, right? But it does exist, and it does show you that the electrons can spread out. This one has a positive charge because they're taking electrons away from it. It's not the only resonance structure you can draw. Instead, you could have also just drawn this pair hopping up here form that. Or you could have done the same thing over here. You'll start seeing a pattern here. You'll notice that these conjugated species oftentimes will not just have like one extra resonance structure, they'll have multiples. So that means, you know, there's a lot of resonance stabilization that can occur here. In general, if you wanted to draw the resonance hybrid, you know that these 4 electrons collectively are sort of spread out amongst all 4 of those atoms. So the resonance hybrid would look more like this. These are all just representations. They're all just ways to sort of demonstrate that, yeah, we can spread these electrons just like peanut butter across all these atoms. Okay? Does that make sense? Very good. When you take something like this, what I'm about to draw, right? That's the one we said was not conjugated. This is what we call an isolated diene. Basically just means not conjugated. Right, this one you can draw a couple of resonance structures. So these in and of themselves are fairly stabilized. You could draw, you know, something like this. Right, but you see, you don't have any other possibilities of drawing them inwards and having sort of that domino effect. So you can have resonance with isolated dienes, but just not as much. And because you don't have as much, they're not as stabilized as the conjugated versions. Okay? Does that make sense? Are there any questions so far? All right. All right. So conjugated dienes, they're not the only types of conjugated species we're going to run into. All right, here's another very important. All right, that's a carbocation, right? It's got a positive charge on a carbon. What type of carbocation is this, if you had to name it? A allylic, yes. Good eagle eye. That positive charge is in an allyl position. So this is an allylic carbocation. And you can put it in the bank now that allylic carbocations of any type are conjugated. We've already seen the double carbons with double bonds have sp2 hybridization and therefore have available p orbitals. What's the hybridization on a carbocation? I'll even draw the H's out for you. What's that? Also sp2, right? Yeah, it's got 3 groups on it. 3 groups corresponds to sp2. And as you can see, we have our 3 consecutive p orbitals. It's kind of messy once you draw all the little overlapping circles. But yeah, those electrons can freely move anywhere between those 3 atoms. So yeah, allyl carbocations. very much stabilized. Just like we saw with conjugated dienes, allyl carbocations exhibit resonance, right? You could very easily hop that pair of electrons over and create a resonance structure. That's what the resonance hybrid will do. Ooh, so guess what this means? We get to update our carbocation stability chart. Exciting. I know that sounded pathetic. It's going to be kind of similar to the radicals, although not exactly. We can have different types of carbocation, allyl carbocations as well, right? You could have something like that. That's a tertiary allyl, right? So just like with radicals, we saw tertiary allyl radicals, secondary allyl radicals, etc. Same thing for carbocations. The stability chart is not exactly the same. Tertiary allyls are definitely the most stable, followed by secondary allyls. I do believe from memory that tertiary non-allyls, I think they're a little bit more stable than primary allyls. They're pretty similar though. And then secondary, and then way back to your primary. All right, so make a little addendum, a little update to your existing carbocation stability chart. Yeah, and we're going to see in just a second that with conjugated dienes, with allyl carbocations, etc., this ability to spread their electrons to different spots, that can certainly lead to some different product possibilities. The advantage of having an electronic book, super convenient. Don't have to carry a big lug a big book around. Inconvenient part, not always easy to scroll through. So give me a second here. See where I'm at. All right. Okay, I want to do this next. All right, so the title is the chapter is Conjugation, Resonance, and Dienes. There's a substantial portion of the chapter that devotes itself to talking about resonance and resonance forms. This is basically a review of stuff we've already talked about. A lot of the stuff we talked about in chapter 1. If you're a little fuzzy on resonance, if you need a little bit of a refresher, you might want to take a look through that. Since we've done it before, we're not going to really go through it, but I definitely encourage you to look at it if you need to. All right. Now, what I want to do is show you just how having a conjugated diene can affect the reactivity of your system. And we're going to do an addition reaction. Specifically, we're going to do a hydrohalogenation. So we can take something like this. It's 1,4-butadiene. I'm going to add some HBr. It's one equivalent of HBr. All right, so you've seen this before, but just not with conjugated diaries. If we did this, well, let's review it. Walk me through this one. This is a chapter 10 reaction. What would happen here, mechanism-wise?
The pi bond grabs the H.
Pi bond's going to grab the H, so the H is going to attach itself to one of these carbons. Which one? The outside one, right? It's going to be a Markovnikov addition. So you're going to go through the most stable carbon cation, which in this case is a secondary. And then what happens? Br attaches to your C+. Yeah. That's old hat. They've done that before. Okay. We're going to be doing similar types of steps here, but there's going to be a few more things for us to consider. All right. Now, looking at this, what's the first thing we need to consider? We know that H has got to go somewhere, right? Which pi bond takes the H? Or does it matter? Again, you're going to see largely going to be a case-by-case basis. All right, what can you tell me about this molecule and its symmetry? Yes or no? Is it symmetrical? Is there any difference between the pi bonds? In this case, it doesn't matter which pi bond you go after. Other cases it might, but in this case it doesn't matter. Let's just pick one. Let's just pick this one. All right? The one on the far right. So you know the one on the far right is going to grab an H. Where is the H now going to go? Is it going to go to the left carbon or the right carbon? What's that? Where? Yeah, why? Markovnikov's rule. Markovnikov's rule still applies, even though you have a diene. All right? So, in this example, you would create a secondary allyl carbocation. Now what happens? Br can attack, yeah. And that gives you this product. Anything else you can tell me here with this product? Did we create any stereogenic centers, perhaps? Oh yeah, this crap again, stereogenic centers. Isn't that a pain in the ass? But everybody goes, yep, yes it is. But it's something you have to account. So again, ask yourselves the eternal question, is there a particular stereoisomer do I get? Do I get a racemate? Well, the answer is always in looking at the hybridization of the carbon as it's being attacked. Here's where the carbon is attacked by the Br. What's its hybridization in that state? sp2, which corresponds to which geometry? Trigonal planar, which means it can be attacked from both sides. Yeah, so you would get a racemate. Does that make sense? Very good. However, we're not done. This is what we call a 1-2 product. I'll explain that terminology in just a minute. That's not the only thing that can happen here. Let's go back to this carbocation. you make that carbocation, and sure, it can be attacked by the BR like that. You definitely will make that product. However, it's not the only thing that can happen with this carbocation. Any guesses on what else, as to what else would happen? Resonance. Yeah, don't forget, we have resonance here. So you can form a resonance structure. And the resonance structure has the form of a primary allo C+. So you do have both forms. This is probably the major contributor, so you probably would have more of this. Well, that depends on the situation. But you definitely have both of them. And so the Br minus could attack while it's in its primary allo form. So you can also get that. And you do. You get both of them. Stereoisomers, yay or nay? Or not? Yeah. Did not create a new stereogenic center. This has two hydrogens on it. So just that and that element. This is what we call a 1,4 product. So yeah, whenever we do addition to conjugated dienes, we always get 1,2 products and 1,4 products. When you see 1,2, that doesn't necessarily mean the carbon number, although it kind of does in this particular example. It just means that the H and the Br get added on the 2 consecutive carbons, right? H went here, Br went here, 2 consecutive carbons. It's like you're counting 1, 2. A 1,4 product is when one of the atoms gets the H, but the carbon that gets the Br is a couple of carbons over. Like in this case, you know, if you say, oh, well, the first carbon here got an H, we didn't get another addition until 2, 3, 4. Right? So that's all that means when we say 1, 2, and 1, 4 products. Okay? Does that make sense? Are there any questions so far? Right. I'm going to erase, well, I'm going to eventually erase all of it. I'm going to keep these up for a second so I can redraw them. Because there's something else we can tell you about these products as well. All right. So we know we can call these 1, 2, and 1, 4 products respectively. However, there's a couple of other terms we can use as well. The 1, 2 product is also referred to as the kinetic product. The 1, 4 product is often referred to as the thermodynamic product. And this is important because we can actually play around with an aspect of the reaction conditions to tweak which of these products you'll get in excess. You know, so doing it a certain way may give us 80% of the kinetic product and 20% of the thermo. Doing it a different way might flip things. Yeah. Think back, kinetics and thermodynamics. You guys have talked about this for years and years in different classes. We talked about it earlier in OChem 1. When you're talking about thermodynamics of a reaction, what are you talking about in general? What does that refer to? People oftentimes don't know the difference between thermo and kinetics. It's not going to be boiling point and melting point. That's more physical properties. Overall change in energy as you go from reactants to products, right? You remember the terms endergonic and exergonic? That's thermodynamics, right? What about kinetics? What does that refer to? It's like, yeah, it's kind of funny. People hear about this for years, but it still doesn't quite register what the differences are. It's very easy to get them mixed up. If I refer to the kinetics of a reaction, what am I referring to?
The heat transfer between them.
That is still thermodynamics. Yes, heat transfer is related to thermodynamics specifically. What's that?
Rate of reaction?
Who said that? Yes, you are absolutely correct. Rate of reaction. How fast does it go? And what does rate of a reaction depend on? Think of your energy diagram. What does the rate of a reaction depend on? Energy of activation. Yeah, you remember that big hump, right? So how big that hump is. The energy hump is separate from the overall energy change between the products and the reactants. Oh, wow. Okay. Basically, to form a 1,2 or kinetic product, the energy hump to get over is smaller. Why is that? The answer to that is actually almost astonishingly simple and practical. Think about this. You had this, then you made a carbocation. You know why the energy hump to make this is so small? It's because of something called the proximity effect. In other words, the BR is over here right next to it already, so it's easy for it just to slip in there and attach. Whereas if the BR had to go over here, whoops, if I had to go all the way over here, it would take more work. It's like if you're laying on the couch and you want to change the channel, the remote is right here on the table next to you, or it's across the room. I know, right? The remote control is the carbon being attacked. The lazy couch potato is the BR lines. I relate to that a lot. So yeah, it's just closer. So that means the energy hump to get over is smaller. Does that make sense? Let's look at the thermodynamic product. When we say thermodynamic product, that means this is a more energetically favorable product than this one is, right? This has a lower overall energy than this. How can you tell just from looking at them that this is the case? You can tell just from looking at the structures, this is more stable than this one. We learned about this a while back.
Is it because the BR is on the terminal carbon?
It has nothing to do with the BR. Oh, y'all are gonna kick yourselves. It has to do with a certain rule, not Markovnikov's rule. Begins with a Z. Everybody stares at me. Zaitsev's rule. What did Zaitsev's rule state? Got the name. That's that's good enough. Zaitsev's rule, just to refresh you, Zaitsev's rule gave you guidelines for determining alkene stability. What's more stable, a more substituted alkene or a less substituted alkene? I think I heard a couple of people say it. Can you say it louder? More. The more substituted your alkene, the more stable it is. This guy is a more substituted alkene. This is a di-substituted alkene, right? One substitution here, one substitution here, 1 + 1 is 2. This is only a mono. So yeah, the 1,4 products tend to give you more substituted alkenes. So that's why they call it thermodynamic. So you can actually tweak the ratios of these by tweaking the reaction temperature. All right. Let's say we ran this at negative 60 degrees Celsius. That's pretty cold. You would definitely get, you know, both of these products. But if you did it at a negative 60 degrees Celsius, you'd probably get about an 80-20 split favoring the kinetic products. Why do you think it's favorable for the kinetic products at low temperature? I'm sorry? It doesn't need as much energy, right? This needs more energy in the system to get over that hump, that bigger hump. Well, when you do this at really cold temperatures, you're really reducing the amount of energy you're putting into the system, right? So, because of that, the amount of product that can form in the 1,4 fashion is reduced. You just don't have enough energy to consistently overcome that energy hump, right? Now, if we change this a little bit, let's just get rid of that negative sign, then they would probably flip. 60 degrees means you're putting considerably more energy into the system. So that means basically either one of the energy spikes can be overcome. And since this is a more thermodynamically stable product, this would be formed in majority. If for whatever reason you wanted more of a 50-50 split, you probably, I don't know, run it at about 0 degrees or 10 degrees or so, somewhere in the middle. But yeah, so this is a good example of just how you can take a reaction that has multiple products, and by holding the reaction temperature at a certain range, you can really increase or decrease your yield one way or the other. Okay? Does that make sense? Are there any questions so far? Let's try another one. Okay, I'm going to make one up off the top of my head, so bear with me. That's pretty good. We'll use HCl here just to be fun. All right, so we're going to approach this just the same way as we did last time, right? We're going to go through the mechanism. All right, first thing we got to do is we got to place that hydrogen somewhere. All right, now there's not any symmetry here, right? So we can't just necessarily willy-nilly pick one of these. We're going to have to really go through and see what individual spot, whether it's here, 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 or here, gives you the most stable carbocation. Play with it a little bit on your paper if you have to. When you think you don't know where you want to put the H, let me know. Oh, wait a minute. Hold on. Oh, I messed this one up. Sorry. It's okay. I can fix it without too much. Bless you. Sorry, I meant to put it right here. Wow, that's a really long methyl group. Sorry about that. All right. Would there be a preferred place to put that H?
The left carbon on the left L1.
Right here? I would agree with that. Because if you do that, you make a carbocation right there, and you'll see that's a tertiary allyl carbocation. That's the most stable one that you can make. And you could try putting the H at any one of these other three spots. None of them are going to produce tertiary allyl carbocations. So for that reason, you would specifically want to form this guy right over here. All right. From there, pretty simple to get the next part, right? We can get the 1,2 product just by having a tack of our Cl minus. And we do create a stereogenic center, so that would be a racemate. What else could we do? What else can we do here with that carbocation? Yeah, you could draw a resonance structure. So instead, you could swing a pair of electrons over in resonance to create a double bond between those two carbons, and then your positive charge will be located there. Cl minus with a tack, and that would give you your 1,4 product. And again, we created a new stereogenic center, so yeah, we would have a racemate. Okay. Does that make sense? Are there any questions on how we got those products? Which one do you think would be major? 1,2 or 1,4?
Because of the high energy system.
Yeah, since we have a pretty good amount of energy, 50 degrees, our major product is going to be the more thermodynamically stable, the more substituted out. All right. Any questions on that? All right. I'm going to let you have the next 3 minutes of your lives. So you're welcome. I actually have to get to a meeting across campus, so I'm going to jet out a little early too. So hope you guys have a great weekend.